So yes, as Tatiana said, this talk is mostly based on my thesis from Ukrainian Catholic University. I've graduated like 5 months ago, but this talk will go beyond my thesis, and I will also talk about some other things. Okay, this way, like human pose estimation and some ideas how this model can be improved. So I will start with what is pose estimation, because it is not so straightforward for those who are not connected with such models. Then I will describe the applications, how this can be used. And third block, I will go into details how to build your own hand pose estimator from scratch, what data you need, what model you should use, how to train it, how to evaluate, and all this stuff. And as I said, like how to improve it if you want better accuracy or make it more generalizable. And finally, some very quick introduction in human pose estimation. So what is what is pose estimation in general? The idea is the following: each object, for instance, hand or human, have some number of key points. These key points may be different depending on the task that you need to solve, depending on the data set that you have. For instance, in the hand, you have 21 key points, by 21 because you can derive the pose of the hand correctly, knowing all these 21 key points, 4 key points per finger, and one wrist. So sometimes it's center of the palm, sometimes it's center of the hand. When we are talking about human have different number of key points depending on the data set. Here it's about 13, I guess. Some data set have labels for eyes, nose, mouth, and ears, so it depends. So the task is to find location of each key point. So not just a cloud of locations, but we want to know where is the finger of the where, like the fingertip of some kind of finger. The same for human. We want to know like exact location of the left foot, exact location of the hand. A key point hand pose estimation can be 2D and 3D. If it is 2D, we need to find the location of these key points on the image plane. If we're talking about 3D, we want to find locations or in a coordinate system of the camera. So camera is like 0, 0, 0, and we want to find locations of key points in this coordinate system, or it can be some kind of normalized coordinate system. Also, it will be 3-dimensional coordinate system. So if you have any questions, you can just interrupt me and I will ask, so you will not miss. Pose estimation is very like wide task, and depending on what exactly you need to do and what resources you have, this can be like anything. Pose estimation can be classified based on the object, whether it's human pose estimation or hand pose estimation. It can be classified based on the dimension or that you want to derive, whether it is 3D hand pose estimation or 2D hand pose estimation, and based on the input data. Also, we have RGB, just usual image. We can depth. I will show this image in a minute. We have stereo image pair. I will show it as well. And we have RGB image plus depth image as input data. And based on the input data, we want to derive like pose of human or hand, 3D or 2D. So on the left side of the slide, there is depth image. This image is one channel image, and each entry has some value, and this value represents how far object from the camera. So if values are white, like here, this means that this object is very close to camera. Black means very far. Gray means something in between. But this values doesn't have like any sense in terms of distance. You still don't know how far the object, but you just know that this human is closer than these doors, probably. Stereo pair is just pair of images. They're made from different points. These points are close to each other. Sometimes they are known how far these points are located, comparing with respect to each other. Sometimes we don't know. So it depends on the, of course, task. So there are some of examples. So it is 2D because we have locations on the image plane, human because humans, and RGB data because it is RGB video. And as you can see here, like eyes and ears are labeled as well. Here is 2D hand pose estimation. Here is 3D hand pose estimation. This is coordinate camera, like 0, 0, 0, here is it, and location of the hand in this coordinate system. And as usual, it's only RGB image. There are some research that are kind of strange for me. You can find pose of some animals, and there is even a paper that explains how to train model if you have some kind of data set with labeled pose of animals. And here is an example of their GitHub project. And also there is an example of car pose estimation as well. Car has key points. They can be wheels, lights, mirrors, doors, anything, and you can just find their location. So we do not restrict only to human and hand pose. Pose can be estimated for any object depending on the task. You just need to find and to understand its key points and prepare the data set. So pose estimation task is very complicated, and it is complicated because of two reasons. First of all, it is hard because you need to think about a very algorithmically complicated model. The model should be able to understand pose, but there is a large variety of poses. The model should somehow deal with self-occlusion, and when it is finger and finger look identically and there is self-occlusion, it is a very hard task for model. Human can have different body shapes, can wear different clothes. So a key point is not about like finding a pattern, because pattern can be different depending on the clothes. And RGB, if you want to get 3D hand pose or 3D human pose from RGB data, there is ambiguity, very high ambiguity, depth ambiguity, because we don't know whether this hand is small and it is very close to camera, or it is large hand and it's far away from camera. It is complicated. On the other hand, there is a problem with data because neural networks requires large amount of data. But for 2D, it is possible, at least it's possible, but very expensive to label the data. For 3D, human cannot label data based on just image. We cannot understand how far key point a person from the camera, because we need accuracy like 2 millimeters. And human are not able to do this. And the data are labeled for 3D. There is a specific camera setup. The camera put in particular positions, and then some calculations are made to find 3D locations. Are there any questions right now? Okay, do you hear me?
Yeah.
Great. So just no questions.
No.
Okay, so next, applications. I will just show one application which I think very cool, but if we will have time, I will show some other projects or cases when you can use hand pose or human pose. So this is virtual reality glasses. It is example, is commercial video for Pimax, but I think other virtual reality glasses have the same algorithm. So when this hand pose estimation algorithm, it is by default in these glasses, and while the developer writes some game for instance, for these glasses, they have access to this hand pose estimation. And when a player plays a game and wants to like take some object from virtual reality, the player can do it just with its hand, with his or her hands, but not use some kind of gloves and anything else, or some kind of sensors. And as you can see here, what is going on, like hand pose estimation is very accurate according to this video, but like in reality, the algorithm doesn't work this way. So don't be so excited about this. But in this case, there are two hands are estimated simultaneously, which is also a complicated task, especially when they occlude each other. How to build your own hand pose estimator? Here is a pipeline for this task. First of all, you need to have some kind of hand localizer. This model will find a hand and crop it on the photo, because it's not a good idea to run hand pose estimator just on the image when there are a lot of objects there, and hand just has very small area of this photo. Then you need to decide whether you want to make your hand pose estimator be like work only for left hands, or whether you want it to work for both hand or right hands. I think better option will be to make it work only for like left hand, and when you and you also need to add some kind of hand classifier, whether it is left or right hand. If it is right hand, you just mirror it and make it look as left hand, put it in your hand pose estimator, and which gives you 2D pose on the image and normalized 3D pose. I will go into details what is normalized 3D pose. Based on the normalized pose, absolute coordinates are restored. And if we are working with video, we want some kind of tracking to make it from to work it from frames to frames. Main goal for my thesis was to improve this part of the pipeline, because hand localization is a simple task. You just can use usual detectors. Classification is also very soft task with very high accuracy. This is very ambiguous for 2D, and it cannot be solved even better than there are existing approaches in the industry. And tracking also soft task. So I worked on this mostly, and I will go into details how to build your hand pose estimator. There are assumptions that you have already an image of cropped hand, and that's it. So this network has two outputs, here and here, for 2D and for 3D. Output for 2D is our heat maps. That is how these heat maps look like. This is heat map is the same size as image, and each point here shows the probability whether key point is present or not present. There are 21 heat maps because I have 21 key points, each heat map for key point. So the 2D predictions are in the form 21 heat maps. 3D predictions are in form of 63-dimensional vector, because like obviously each key point has 3 coordinates, x, y, z. We have 21 key points, so it will be 63-dimensional vector. It will be just flattened. Data preprocessing. First of all, data processing with image. If a data set allows, you can do some kind of background augmentation. You need to crop image as close to the key points as possible, so there are less background in the image, and model will be more accurately. I trained model on this size of images. It is enough because hand is not very so detailed and complicated object. And if you use some kind of pre-trained model, I used ImageNet, ResNet trained on ImageNet. I used normalization. Next, for dataset has coordinates like numbers only, but I need to convert them to heatmaps. So I created heatmaps. Heatmaps are in the range from 0 to 1. I think I will have a slide how to create this. No, I will not have. But how you create, you put 1 in the location of the key point, then you add Gaussian blur, and then you normalize, so the maximum value will be 1. Because when you blur 1, there will be lower values than 1. And as a result, here will be 1 and like 0.9, 0.8, 0.5, and zeros in the other locations of the heat map. So entries are from 0 to 1. And 3D location, first of all, I normalized absolute hand pose. Normalization was done because normalization decrease of freedom, which neural network need to understand, like depth and size in our case. So I put this key point in the center of coordinate. So I shifted the hand, so this is 0, 0, 0. And then I normalize it, made size normalization to, so distance between this key point and this key point, 10 and 1, is equal to 1. And as a result, the vector will be of size 63. And I trained model with using different datasets, and not all the datasets have 21 key point. So I need to have like kind of ticket whether we have this coordinates for this key point or not. So to make training be possible with partial label data. Dataset is a big pain in hand pose estimation, because there are some good datasets, but they are synthetic. There are about 7 datasets. Most of them are not good for this task because because several reasons. I selected only these 4 datasets. 2 of them are synthetic. They are very large datasets. They have good labels, very accurate. They have 21 key points, but there is still very large domain gap between hand pose, between hands in these synthetic datasets and between real hands. On the other hand, we have real datasets, but these real datasets, they are video sequences, and in video sequences, images are very correlated. There is just a couple of actors there. Hand is always the same. Pose of the hand is similar between these frames, and this real datasets, they don't have 21 key points that I need. Here we have only five key points, only fingertips. Here 21, but the last one is palm center. It is not what we need. So I try to solve a task how to train a model and make it work on real data, having good synthetic data, not so good real data. Do you have any questions right now?
The fact that you have labels in video format, you said it's like a drawback as a really highly correlation between the different frames. But from other hand, this could be useful for the video processing. So did you focus only on image, like try to estimate the hand pose, or the main goal was just to work with video?
Mm-hmm. So as I showed here is part tracking. I didn't focus on this task. I focused only for this. Video frame means that here we have like 300,000 images, and all these images are different hands, different colors of hands, different poses. Here we have like 18 and 3, and all these images, they are part of video frame, so they are much less like lower number of unique images here. So the numbers here even smaller if we are talking about.
So it's not a number of videos, it's number of frames in the video.
Number of frames in all videos. There are about like 4 or 5 videos.
Okay, thank you.
Let's move on. So my architecture. I used some kind of UNet-like architecture. Why? Because I need to restore the actual size. I want 2D. I wanted input to. I want this network to input 2D heat maps. The heat maps are the same size of input image, so I need to restore the size, and I used UNet. Encoder was ResNet. Decoder was just built by hand. It is mirror image of encoder. Yes, and why I used ResNet? Because I used we made some experiments and decided and saw that pre-trained on ResNet on ImageNet this encoder part works much better. So the same image. More details about losses. I use two kind of losses. For vector, I use just usual mean squared error applied to vector. For heatmap, I use intersection over union. It is very good loss. Interesting thing that in the papers I've researched, nobody uses this loss, but my mentor said that probably they use, but they do not disclose all the details that they have. So it is the loss. To use it is just usual intersection over union, but this loss can be applied to continuous data as well, as in our case. And also, when losses are in different scale, you should add some weighting. When I do it, I just train model for several epochs and see the difference in scales, and just add some coefficient to make the difference in scale be not so big, or even losses should be equal. Very interesting thing, and I use it several times in SoftServe, how to train data when you have with partial label data. When you have data for all the key points, first of all, you calculate loss for every key point, comparing predictions with ground truth. Then you average losses for image. It will be image loss, and then you average image losses in the batch. It will be batch loss, and you propagate gradients using this batch loss. But in my case, there are some data sets that do not have all the key points. I have, for instance, only fingertips. What I do, I calculate losses. For this non-existing key points, there are like 0, 0, 0, or 0, 0, just zeros. I calculate loss for like ground truth. I calculate loss for all the key points. After that, I have a ticket, which key point I have and which key point is absent. Then a ticket is whether 1, 1 or 0. So I zero all the losses. I do not use all the losses but I do not use losses of non-existing key points, and I calculate mean only for those losses that are present in the dataset, only for like 5 fingertips, and it will be image loss. And finally, I average all the image losses in the batch. This technique is very cool because, for instance, if you have a very non-typical dataset split train validation, you can use as well. For instance, you want to have an image and you want split image like by using the diagonal split. Left part is train and right part is validation. You can use this approach as well. We have CNN that outputs heatmap, but we need to restore 2D locations. There are two approaches. This is heatmap. We can just select the maximum value, that maximum XY value, and make it be 2D locations, or we can calculate 2D mathematical expectation to find the location. We're just waiting. Here is an example. This is our heat map, and we calculate sum by y coordinate. It is kind of votes multiplied by exact y coordinate 0, 1, 2, 3, add, and the result will be location, 2D location. The same for x, we just sum all the votes for each location, multiply, add, and the result will be, and you round it like to 1, 1, because we have only pixels, but not just. I also used several data augmentations. I used it for synthetic and for real data set because there are not so many data. I did almost everything that was possible. Background augmentation, because some data sets, they had mask for hand. Brightness, random change, contrast, saturation, Gaussian blur. Just to pay attention that some augmentation they change only image, some augmentation may change image and 2D location, and some augmentation change image, 2D and 3D location. So just pay attention and change other locations appropriately. This is experiment 1. I trained model on synthetic dataset and evaluated on synthetic dataset as well, on 2 synthetic datasets, and I get very good results. So the model was really simple, but the results were kind of good. So there are errors for these 2 datasets. This means that there are about 2% deviation on average for key point, from prediction to its ground truth per key point. And this means that there are 14% deviation in 3D. This is like 1, and 40% of this distance deviation from prediction to ground truth. These results are good, and in case we have very perfect large real data sets, that what we can achieve. But in reality, we don't have this data set, so these numbers are just hypothetical numbers. Here are examples of predictions. This synthetic hands from the data set from 1 and 2nd, and this for this hands model worked fine. Prediction error is very low. All the key points are visible. Hand pose is very good and natural. And here example for the here examples of from the data set where a model has very high prediction error, and a lot of hands are occluded with different objects, and in this hands in this data sets, hands don't even look like hands, because they were created using GANs to make it look like real hands, but in reality we have some kind of monsters. And also the model was trained with these examples as well, so in case you have only good examples, the accuracy can be even higher. Yes, that's it. Next, what I did, I tried to fine-tune model trained on synthetic data with some real data. There are 2 real data sets I used, Stereo and Dexter. They consists of like 5 or 10 video sequences. I trained model on like 5 sequences and evaluated on 2 other sequences. And this is the same as here. I trained model on 4 sequence and evaluated on 1 sequence. Yes, that's it. And the results, as you can see, when the model was trained only on synthetic data, the results were not very good. It is 2D error, like 10% deviation from ground truth to prediction, and 20% difference between ground truth and prediction. But when we fine-tuned with real data, the error decreased. I couldn't conduct the same experiment for 3D because we don't have enough key points, and we cannot derive normalized hand pose. So the experiments were done only for 2D data. There are some interesting observations that I mentioned. First of all, model could make predictions for absent points, for absent key points. What does it mean? In this Dexter dataset, there are labels only for fingertips. When the model was fine-tuned only for fingertips, it could understand where other key points are located. So the CNN was able to understand the ball spatial structure of the hand, which is kind of cool. Like, here is an example. Model was trained on this. Location of wrist is pretty correct. Location of all the other finger key points is pretty correct. Another very interesting thing is that model can change. Model can understand the change in labeling. What I mean, the model was trained on Synhen's dataset, and as you can see, labels here are like joins. And the model was fine-tuned on the stereo dataset, and here labeling is a bit different. Yes, here is like labels center of joint of the bone, but here we have joints. When the model was fine-tuned and made predictions, it could also make predictions that are similar to the ground truth. So the labeling was shifted. And for 3D, remember I didn't have any ability to fine-tune model with 3D data, so it is only predictions on real data. Model works fine for very simple poses like here, and model fails in almost every other case. But as well, very nice observation that model, even when it fails, it outputs hand that is left hand, and the joints and angles they look natural. And conclusion from my thesis, but not conclusion for my talk. So the absence of the data is the main problem, because as you've seen, I trained model which was very simple. It is just simple UNet with a ResNet encoder, and the model was able to predict almost perfectly on the synthetic data when it trained on synthetic data. But model trained on synthetic data cannot generalize well. There is still large domain gap between synthetic and real data. Fine-tuning model can be a solution. So fine-tuning decreases 2D error to 3-4%, which is kind of nice. I assume the same will be for 3D data. There will be can be also decreased, but they didn't have chance to check this. And some links to my thesis text and to my GitHub project. Are there any questions for this part? Do you still hear?
Yeah, thank you. We are here.
Great, because I'm sitting in the empty room, okay. talking to somebody, and I don't have don't hear any feedback. I feel very strange.
Don't worry, we're very careful.
It is not the end, so we can continue. So it was a very simple model, let's call it baseline, and there are some ideas how this model can be improved. I tried only some of these ideas that I will show you right now, and there are some ideas that I just find close to deadline and obviously didn't have time. So if you're going to work with human or hand pose, try these ideas. I think they're very, very good. First idea that I really like is domain adaptation. This scheme looks strange, but in reality, it is very simple, and the idea is very simple. This domain adaptation helps you train the model when you have a lot of labeled synthetic data and when you don't have labeled real data or partial labeled, as in my case. There are three parts: feature extractor. This part, let's call it hand pose estimator, and this part is domain classifier. This part outputs all the key point locations. This part outputs whether image is from real or from synthetic datasets. When you train this model, you train it in several stages. You want to minimize the loss, classification loss, updating this loss and updating these weights and these weights. On the other hand, you want model to be able to correctly classify whether model from was the image from a real or a synthetic data set. You minimize this loss, updating only these weights in correct way. On the other hand, you want model to learn domain invariant feature. So you also maximize this loss, the same domain loss, by updating these weights. In such a way, model learns domain invariant features. I didn't have chance to try this, but I think it is very good things to start with or continue with, as in my case. So these results are from this original paper. I put a link here. So when the model was trained, there are two domains: source domain, which has labels, and target domains doesn't have any labels. This data like with no labels. When the model was trained only on source domain and predictions were done for these target domains, the accuracy is so low. When the model was trained in usual way on target domain and prediction were done for target domain, the accuracy is such high. So it's like lower bound and upper bound. But when the model was trained using the domain adaptation techniques, having only source labels for source domain and target unlabeled, the accuracy is significantly higher than when it was trained only for source domain. And there are several data sets. It works with just numbers. Of course, these data sets are very simple, but the idea is very nice. So in some cases, the performance even close to this situation when the model was trained only on target domain. Next one, Latent Heatmaps. It is a very new research paper in this field. Usually we do predictions using just direct heatmaps. They're called direct heatmaps. But the authors of this paper, they ask several questions. And for instance, how should we choose blur radius for blurring? Should the blur be like round, or maybe it should be ellipsoid? Should blur be the same for all the key points? So there are a lot of hyperparameters that we choose when creating these heat maps, and we cannot test whether these hyperparameters are good or bad. So what this author propose? They propose let model create heat maps on its own. And here I will show in the next slide how they did it. But here are examples of I tried this approach. Here are the examples how model derived heat maps for key points. So as you can see here, for instance, it has such form here. So model tries to find the location of key points and finds a path where this key point can be located. And the same for finger. So how this was done? It is all the CNN. It outputs some intermediate feature map. Then we applied to this feature map also some convolution and the softmax. Softmax is applied for each heat map. So softmax for one heat map, softmax for another heat map, so the values of the one heat map should sum up to 1. Then we calculate the average, as I showed you previously, using the 2D mathematical expectation, and create a vector. Then we applied mean squared error loss. We have the same ground truth vectors to this, and propagate the gradients. And when you visualize this layer, this heat maps, you'll receive the result that I've shown you just. What I think about this approach? Well, it's nice because the performance for this wasn't significantly better. It wasn't better at all than for usual heat maps. It was comparable, but you do not have to create the heat maps on your own, which means you don't have to store these heat maps in memory during training, which means you can use larger batch size and train model quickly. Then you do it with 2D heat maps. But usual heat maps, direct heat maps, they're state-of-the-art approach for 2D, and most people use this direct. Nobody uses this latent, but I think it's a very nice idea to try. Next, these authors of these papers, they tried to create 3D heat maps. When you train models using just a vector, it is kind of, for neural network, it's complicated to find some spatial relations between key points because model sees just numbers. They proposed to create 3D heat maps. It is an example of one heat map for one key points. There are 21 such key points. They have very, very large structure. They increase the dimensionality of these key points. This approach, according to the authors, is more accurate than just vector approach, but it cannot be used in real time because a lot of computations are required. And finally, the last approach is, let's consider a hand as a tree. I also tried this approach. I didn't receive very good, significantly better results than using just usual vector, but it is a very interesting approach as well. So when I yes, when you think about hand pose 3D locations of key points as vector, you have 63 dimensional vector. Yes, sorry. How to represent a hand as a tree? We have key points and have the locations, and here are the yes, and here will be bones. And now we do not estimate the location of the key points, but estimate the locations of bones. Originally we have 63 dimensional vector, but right now we have 60 because there are not 21 key points, but 20 bones. And these bones are vectors. Yes, how to calculate these vectors? Like in usual way, this is the center of the coordinate. These black arrows are, we have these black arrows, they are known because we have locations of these key points, and the key points location can be represented as a vector pointing from the center of from the origin to this key point. And just using the vector summation vector rule, you can derive these bones. And so each vector is represented using XYZ coordinate. And when you make prediction for a particular key point, you just sum all the vectors along the path. So if we want for 21, we sum 17, bone 80, 90, and 20. So this one. Finally, there are a couple of useful links. It is very interesting GitHub group. They save all the recent works, papers, and and datasets and codes in this group. So if you're working with this hand pose estimation task, just go there and find something interesting for you. And very quick introduction to human pose estimation, like the same algorithm as for hand pose. Even when I was working on my thesis, I used a lot of approaches for human pose estimation because human pose is much popular than hand pose, and they have a lot of things. And maybe that's it. Yes. Do we have like 5 minutes?
Yeah, I think so.
Let me show you a couple of examples where this hand pose estimation can be used. This is project. The idea is to recognize sign language. They do not use hand pose estimation to recognize gesture, but they use human pose. Why so? Because depending on where the hand where the hand located when showing some sign, it can affect the meaning of the sign. So they, according to this video, they do something with human pose estimation, and they have a lot of charts like there. And they say that this works in real time. They can easily translate from sign language to just text. Also very interesting case when like girl trying to rent a room in the hotel, and they tell something, there is camera, and it translates everything to text. Next approach, it is a game for game console. There is Kinect. Kinect is a device that makes it that is able to understand some voice commands, some signs, and recently last versions are able to understand human pose. And here is example. It is for training. The guy is doing something. His virtual avatars do the same, and then he receives feedback from the trainer whether he does something correctly or not. Maybe he should do something differently. But this still doesn't work very, very well. But at least some research were done. And finally, this is example from paper, but human pose estimation can be used also for animation. You can animate some character with with less efforts than you do it manually. And yeah, that's it.
Okay, thank you, Ola. Do you have any question? Colleagues, do you hear us?
I have one quick question. So when you train the model, just maybe some basic model in 2D, do you have some problems with like maybe unbalanced classes, or I don't know how to say it, like one key point is detected much more accurately than in others, or not such a problem?
I didn't make the comparison between key points, how accurately they detected comparing to each other. Probably there are some, like for models that are easier to detect, other not. Class imbalance, yes, actually there is very strict class imbalance in this task because we need to detect one single key point and all the background. So but if we use intersection over union loss, this loss is magical. He deals with all these problems. So there is no such class imbalance issue here.
Okay, thank you.
More questions?
And like results you received, how are they like in comparison in what we have in research now? So
for 2D, they were very close to, even they were similar to what other did. But on the other hand, it's just very hard to compare because they use different data sets. They use different, like some of them cropped hand, some of them do not cropped hand. But with what I can compare for 2D, they were very similar.
okay.
More questions?
Ola, do you know if there are any RNN-based approaches for dynamic pose estimation?
You mean like video sequence?
Yep.
I don't know about RNN, but I know how they do it with CNN. They just add restrictions for the next frame. They know where the key point was in the previous frame. They add some like restrictions that key point cannot change a lot. And they made some smoothing also. But for RNN, I haven't seen anything.
Okay, and the restrictions, if you know, like in few words, more of the technical side, how it works.
Okay, we have, for instance, we have. I will show you some slide. Which one? That would be like this. How they do it? They run hand pose estimator on this frame. When then they usually they run pose estimator. It also depends whether we are tracking in real time or based on the video. So the approaches can be different. Let it be real time. We receive the frame. We know the location of the previous frame. We made estimation, and we assume that the hand pose didn't change a lot. So there is, I think I have the slide, maybe. I hid it, but I have it. No, I deleted. Sorry, I don't have the slide. So the idea that that they add some post-processing, they create some kind of penalty function. To this penalty function, they add how new predictions are different from the predictions in the previous frame. And if it is like very large, yes, they like restrict.
Okay, so thank you. I get the idea. So it's kind of a additional loss for big deviations. Okay, thank you.
Mm-hmm.
Any more questions? Okay. Do you have any questions? No, I think. I have one more. Ola, could you please explain us why did you decide to use different representation of target for 2D and 3D cases? For 2D, as far as I understand, you use Heatmaps, and for 3D case, it was set of coordinates. Yeah.
Yes. Why the question? Why we don't use?
Why did you use a different representation of your target? For instance, why did you use Heatmap for 2D instead of set of coordinates, for instance?
We can use 3D Heatmaps for 3D coordinates, but the computation will be. We need a lot of. It is very computationally intensive algorithm. So in the research community, right now the state-of-the-art approach is 2D Heatmaps, and for 3D it is vector. I also tried different representation. I tried Latent Heatmaps for 2D, and I tried vector representation for 3D, but the results weren't better. So I just stick with what is state-of-the-art.
Okay, thank you. Any more questions? Thank you, Ola. It was a very interesting speech. The record, I hope, will be available in our conference page. As for our next speakers, I'm not sure, but I try to figure out who will be next. Thank you, Ola, and have a nice evening.
Thank you very much. Goodbye.
Thank you. Bye.